welcome everybody. Today we have the pleasure to continue the course titled Density Functionals for the Kinetic Energy Theory and Practice, presented by Dr. Paul Ayers from Macassar University in Ontario, Canada. Welcome, Dr. Ayers. Please go ahead with the course. Thank you.
Okay, so thank you. And with apologies, because I talked to Alberto and Jose Luis about what I would talk about, and this isn't kinetic energy functionals anymore. I don't know of a unifying theme, except perhaps that these are the two topics that were probably most current when Jose Luis was a PhD student in Johns Hopkins, right? Where probably these two topics were the two things that were most in the air. So we're going to talk about these two things. And I'm going to talk a little bit about reduced density matrices. How many people know something, have seen reduced density matrices? Is this very new to people or not? Okay, somewhat new. So anyway, I'll go gentle, right? And we'll talk mostly about one electron reduced density matrices. At the very end, this will get into something that's a little bit edging towards the modern research, but for right now, it's going to be very general. So the next slide. Okay, so I wanted to start by saying that this goes into the family of, we're trying to solve the Schrodinger equation. This is my Schrodinger equation, right? Everyone here probably has heard this famous quote from Dirac without the last sentence, right? The last sentence is sometimes not included in this quote. Just, it says, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. And then often people stop, right? But the next sentence was, it therefore becomes desirable to have approximate practical methods of applying quantum mechanics, right? So that's what we're going to talk about today. Okay, next slide. Okay, so this is your Hamiltonian, right? You have a one-body piece. It has kinetic energy, electron nuclear attraction, can have other things in it, like an external field, things like this. There's a two-body piece. That's the interaction between the electrons, right? And if you're dealing with nuclei or helium atoms or something, then there could be other terms here, right? But for electrons, it stops here, right? So for any elementary particle, like electrons, there's only two particle interactions. This is universal. If I tell you we're dealing with electrons, right? The only thing that changes is this piece of the problem, right? And specifically the electron nuclear piece, right? And I just put this in for interest. This is really written in a non-relativistic way, but two-component relativity really is no big deal. It amounts to fishing around with this and maybe fishing around with this, but you just sort of change your operators, right? So up to really very relativistic cases, we have to solve this problem, right? This is what Dirac meant, is we just need to solve this problem. So next slide. There are a few things that we should say about it. One is that, it's an eigenvalue problem, but we usually don't need all the eigenvalues. We just want a few of them, the low energy ones. We need incredible accuracy. So, typical molecular energies, I say 10 to the 2 to 10 to the 3, but they can easily be 10 to the 4, 10 to the 5, 10 to the 6, depending on how you molecule. The molecular energy grows linearly with the size of the molecule, right? It's an extensive property. But we need chemical accuracy, which is 10 to minus 3 error, right? So we need absolute error of 10 to minus 3, right? And sometimes more, right? If you want to do spectroscopy, you may want 10 to minus 6, right? So 10 to minus 3 is sort of our starting point for useful chemistry. We talked about that with the kinetic energy functionals that, I was showing you errors that were order 1, and it was like, not so great. 10 to minus 3, that's where we're trying to get. A relative error of 10 to minus 3, so not absolute error of 10 to minus 3, relative error of 10 to minus 3 is trivial, right? I do it on the calculator. It literally just take your molecule, add up all the atomic energies. That is your molecular energy to 0.1%, right? So obviously that's all the chemistry is below that 0.1%. Right? Okay, next. Right? So maybe actually go back one slide for a second here. So the other thing to say here is if you think about what this equation is, this is just a partial differential equation that we need to solve. It's a linear second order partial differential equation. Superficially, this is the easiest thing in the world to solve, right? This is like classic mathematics from the 1800s, right? Dirac knew what he was saying when he said it was hard, right? The number of dimensions is gigantic, right? And the size of these quantities that we need to look at, the size of the wave function, literally easily spans 6 orders of magnitude, right? So it's a very strongly peaked solution to a very high dimensional differential equation. So solving this, you don't want to just say, hey, I brute strength this, I put this on a grid and I solve it. Not a good idea, right? That will kill you, right? So we need to be clever. So now, next slide. And so we put in a basis set. And the tradition is we put in a single particle basis set, right? And we all use L for the number of levels. I hope I was consistent throughout the talk for L as the number of levels. I may or may not have been. And basically you say, okay, now I need to know how to put N electrons into L levels. That's what we're saying. And we just discretize our Schrodinger equation. So we have to do some integrals. We project the 1 electron integral onto the basis set, and then we project the 2 electron integral onto the basis set. And just to give you an idea of what we want to do, like 30 electrons with a few hundred orbitals is routine, even for very, very, very accurate calculations. Doing something with, more like 100 electrons and 500 or 1,000 levels at very accurate level is not that much. And let me just see. That's okay. We're going to just go to the next slide. Be fine. Ooh, maybe we go to the next slide. Can it go? Yeah, thanks. Okay, so we're not going to do this. We're going to we have a trick. And this is called second quantization. People have seen second quantization. They see nods. Okay, that's good. Right? So we say basically that Q dagger means create an electron in the orbital labeled Q. And P dagger means create an electron in the orbital labeled P. Sometimes people say AQ or AP, and I'm not going to because I'm lazy, basically. And the A is redundant, right? It's just that orbital we create or remove. I write them like this so that it's clear that everything I'm going to tell you today, or almost everything I'm going to tell you today, it doesn't depend on whether we're dealing with fermions or bosons, okay? If eta is 0, this is bosons. If eta is pi, this is fermions. Does anyone know what you call it if eta is not 0 or pi? So if it's not 0 or pi, then these are anyons, right? So it doesn't even, everything works, right? Now, anyons don't really exist, like there are no elementary particles that are anyons, but sometimes you put together a bunch of electrons or a bunch of bosons or a group of electrons and bosons together, and then that acts like it was an any, right? So it's a quasi-particle intrinsic excitation. And these are the rules basically for how to manipulate. And so instead of doing all of this calculus, we've turned this into a problem in algebra, right? And you either feel good or bad about that, depending on how you feel about algebra. But for a computer, algebra is much better than calculus, right? So we have mapped this onto something for a computer, right? Next. And Okay, so we're going to talk about density matrices. And this is just the definition of a K particle density matrix. We'll think usually K electrons because we usually care about electrons, but K particles. So what does it mean? It means I pick K orbitals and I remove an electron, and then I pick K orbitals and I create an electron, and then I add them up, right? For any wave function, I can compute this quantity. And then I'm going to make a weighted average of these to form a density matrix. So my state, right, is always described in terms of wave functions. If it's a pure state, it has one wave function. If it's a mixed state, it has several wave functions, right? If it's a mixed state, then you get this density matrix, right? If it's a pure state, there's only one term in the sum, one of the W's, right? And what we say nomenclature-wise is that if there exists some size in W's that give you this gamma, then it's irrepresentable or ensemble irrepresentable. If there's only one non-zero W, then we say, okay, there is one specific psi that gives me this gamma, then it's pure state irrepresentable, right? And there's practical conditions we know only for K equals 1 and K equals N. K equals N is trivial. K equals 1, I'm going to show you. So K equals 1 is an easy case. And just when K equals 1, traditionally, instead of using the big gamma, we use a little gamma. So to just be very clear, what I'm calling gamma PQ is equal to big gamma of P1. Right? So that's just notation, right? So I described you. Now, there's some things that we should think about here. Number one, I'm asserting, should maybe change my pen color. I'm asserting that this is a closed convex set. So the set of irrepresentable ones that are closed and convex. That's one thing I want to think about. I'm also, well, that's the main thing I'm asserting on this slide. So next slide. Next, yes. Okay. So okay. So now we're into this one density matrix functional theory, right? So maybe what we're going to do is we're going to sort of take a pause here, and we're going to, on the next slide, I'm going to talk a lot about, I think my next slide is a slide that I'm designed to write on. We know the Hornberg-Kohn theorem. Hornberg-Kohn theorem says, if I give you a density that's a legitimate density, right, then it corresponds to at most one potential, right? It might correspond to 0 potentials, but it never corresponds to 2, right? Now, there's a footnote here, which is that it's not true if you have magnetic fields. It's well known even for density functional theory. In density functional theory with magnetic fields, you can have multiple magnetic fields that give the same density, but you have multiple Hamiltonians that have the same wave function with magnetic fields. And so we can't talk about this. We're doing things without magnetic fields. And I'm also, so if I give you a one-body operator here, right? And I add a piece of the identity matrix that's just shifting the whole Hamiltonian by a constant. And shifting the whole Hamiltonian by a constant doesn't change anything. And so when I say there's only one H that gives gamma, I'm not including H's that are shifted. This is just like in DFT, right? You say, oh, well, every density corresponds to one external potential, but a constant shift in external potential I don't count as different external potential, right? Right, so the zero of energy scale is an invariant, and gamma doesn't depend. Okay, so next slide. Okay, so now I'm going to do some proofs, right? So I'm going to think about a few things that we would like to do. One is, I'd like to understand that I'd like to understand that the irrepresentable set is convex, right? I'd like to understand something about what are the conditions for something to be irrepresentable. And I'd like to be able to look at this Gilbert theorem, okay? So let's start just by, I'm going to write down my energy in terms of my density matrices, okay? So I define gamma of P1, Pk, P1, Wi, and I said it would be and, um, okay. So this is my requirement. There's another requirement because this is a mixed state. So this is a sum over I. And I also require that the sum over I of Wi is 1 and that all the Wi's are non-negative, right? So this is just to say these W's are the probability of seeing your system in the state I. That's what W's mean. The probability of seeing a system in a state has to be between 0 and 1, obviously. And the sum of the probability of seeing the system in all the states, as in the probability the system is in some state, has to be 1, right? So this is just intuitive, right? Now, the thing that was missing from that last slide was to write that the energy I can write now as a trace of H gamma plus a trace of V gamma, where this is the one body term and this is the two body term. Okay, this is the exact expression for the energy, right? This piece is, say, the electron-electron piece. It's the piece that has two particles in it, and the other piece is the piece that is not, is one particle, right? B plus, right? So if we think back to the 1950s, roughly, this was really exciting because we said that it was very hard to do the Schrodinger equation. But this seems really wonderful. This says, well, this looks like a two-particle thing. This looks like a two-electron object. And it said, well, we should be able to do this sort of theory with many electrons. They just look like two electrons. We're just going to do, you know, E of the ground state is equal to the minimum of gamma and gamma such, well, at the beginning, let's just say the minimum of these. Okay. And so everyone just said, we're going to do this, and was done back in the 1950s. And the result that they got was way beneath the true result. Way beneath the true result, right? For something like the beryllium atom, instead of getting minus 14.6, they got like minus 28, right? They're even worse than orbital-free DFT results, like really, really bad. And the reason is that we forgot that these density matrices have to come from a wave function, right? So then we go back and we say, okay, let's assume that the density matrices come from some choice of W's in size, right? I don't care what it is, as long as one of they come from something, right? And then this becomes an equality. This works. But you have to come from this, which is equivalent to what we said, gamma and gamma. Okay. It's equivalent to saying they're irrepresentable. That's what irrepresentability means. So now I want to understand this irrepresentable set, right? So the first thing I'm going to do is I'm going to try to understand what does it look like? And the first thing I'm going to show you is that it's convex, right? So what does it mean for a set to be convex? A set is convex if, and I'm going to be specific for the little gamma, just because that's what we're going to care about most, but this works for any gamma, right? It works for, it doesn't matter which type of gamma you're using, right? So okay. So I wrote this mathematically, but we're just about to explain it computationally or pictorially, right? Because this is just a proof by picture, right? If I give you a convex set is something that looks like this. A non-convex set is something that looks like this, okay? So this is convex and this is not convex, right? If I give you two elements of the set, then this is just a line, an interpolation between these two elements, a weighted average of those elements. And this is saying that every piece along that line is inside the set. And that was clearly not true here, right? There were things that were between these two, weighted averages of these two that were not inside the set. So it's not convex, okay? So now I just have to understand, is it true that this implies that the density matrices are a convex set? It will be nice for me. It will be very important, in fact, that it's a convex set, okay? Okay. So now, what does this mean? Gamma 1, right? My first density matrix. I'm going to be a little bit sloppy with it. Well, maybe I don't need to be sloppy. Let's just write it here. It's going to be P1, well, P, no reason to write P1, Q1. We just write P and Q. because I assumed that gamma 1 was irrepresentable. So it looks like this, right? And now gamma 2, also irrepresentable. It has different weights and different states. Okay. So I just used the definition here. I took a weighted average of them. But now let's think about what it is. This is the sum over wave functions. The only thing I need to prove is that sum of t times wi of 1 plus 1 minus t wi of 2 is equal to 1. And that t, well, okay, so that's the first thing to prove. Let's prove this first. Okay. So this is obviously true. The sum of the wi's is 1. The sum of wi2's is 1. T plus 1 minus t, the sum of that is 1, right? So first piece of this is true. The second piece is that these numbers need to be between 0 and 1, right? Now, at first you think trivially true, right? Because I multiply by a number between 0 and 1, and then you multiply, that number was between 0 and 1. So the product is also between 0 and 1. And here, there's a number between 0 and 1, and you multiply by a number between 0 and 1, and that product should be between 0 and 1. You need to be a little bit careful because there's nothing that guarantees you that the wave functions here don't also show up there, right? Right, there's nothing, we made no assumption that these wave functions were orthogonal, right? And you need to prove that even if the same wave function showed up in both places, right, that somehow it would still have this form, right? So let's just assume that one of the wave functions, let's say the kth wave function, shows up exactly twice, right? And then you just have to say, well, that would mean 1. I need to prove, well, it's obvious that this thing is not going to be less than 0. So this thing is obviously greater than 0. I need to prove it's also going to be less than 1, right? But this number is less than 1. This number is less than 1. So I can just write this as wk of 2 plus t times wk of 1 wk 2, right? Okay, so now I can start thinking about the worst case scenario here for me. So the worst case scenario here is that wk of 2 is, well, if this is 0, then this is fine, right? If wk of 2 is 1, then I add 1 here and I end up subtracting 1 off here, still fine, right? So you go through this and you go, okay, this is actually also, even in the case where this thing shows up twice, because you're taking a weighted average of 2 things that are less than 1, and a weighted average of 2 things that are less than 1 is also less than 1, right? So this is less than 1. So that proves it's convex, right? So just curious. Okay. Okay, so we proved it's convex. We haven't talked about the irrepresentability conditions of a Gilbert theorem, but I'm going to rather than erase the tedious way, I'm going to erase the easy way. Okay, so what are the irrepresentability conditions then? So we have a convex set. Looks like this, right? I want to know something. I want to know a way to know when I'm not inside the convex set, right? So I understand because these matrices had all the information about what I want to do, that if I minimize let's write it this way. That's the ground state, right? By definition, right? I minimize over the whole ensemble. That gives me the ground state, right? Now, the same is going to be true if I give you density matrices such that the density matrices come from some so if the density matrices come from some expression, this expression here is just equal to the trace of H on the density matrix. So as long as I minimize over density matrices that have the same domain, the same variational domain as this principle, I will also get the ground state. So this is also the ground state. So that's one important thing to understand. The other important thing to understand is that if I give you a point, let's just call this gamma tilde, right? That's outside the set, right? Then there's always a way to divide it from the set, right? So there's a and we don't need to prove theorems here. We just do it by construction. It says there's a hyperplane such that on one side of the hyperplane you have your convex set, and on the other side of the hyperplane you have your point, right? And the expression for a hyperplane is exactly right a linear operator on gamma equals some value, right? That's the definition of a hyperplane, right? A plane is linear, right? We have something that looks like that. This is trace of H gamma, right? Right? So what does this mean? Well, over here on this side of the set, by definition, for gamma that are irrepresentable, trace of H gamma equals, well, is greater than or equal to the ground state of H for every gamma. So what it says is I pick any gamma, anything inside this set, and when I apply it into the variational principle, I always get energy that's too big, right? There'll be one place, this is equality, when it's exactly equal. What is the equality? The equality corresponds to a point that just touches the boundary, right? That's a supporting hyperplane for the convex set. This set, there's a hyperplane, looks like this, and on one side you have your real space, and on the other side you have your things. And so what that says is if stopped working. The screen stopped working. I forget, we had to do something yesterday. I think it just froze. But it's not with my finger either, so. Yep, that's okay. Yep, that's fine. Oh. The screen doesn't like the math either, so it's okay. Okay. So let's go back to what we had here. This is trace of H gamma equals E ground state, right? That's one of the cases where it's a supporting hyperplane. All of these states, actually, why have a fancy setup and not use it? All of these states satisfy trace of H gamma greater than equal to E ground state. And then a point over here, gamma tilde, okay? So what it says is there's at least one Hamiltonian for which a non-n-representable gamma gives lower than the true ground state energy, right? So when I think about this, I think we have lots of density matrices. These are the sick density matrices, right? These are bad. They don't correspond to a real system. And what this says is there is always at least one Hamiltonian. You can think of this as the doctor. There's always at least one doctor that can tell you that this is a sick density matrix, right? Right? It's worse than this. So suppose you give me a non-representable density matrix. And suppose you tell me that I'm willing to accept anything as long as the energy is not off by more than 1 billion. There will always be a Hamiltonian for which you will be off by more than 1 billion. So what that says is if you're non-representable, there will always be a Hamiltonian for which you have an error that is as big as you want it to be. Which means that if you want to do chemistry, you better not have non-representable density matrices, right? And it's really simple, hypothetically. It just says, okay, just make sure that for every Hamiltonian, you always get bigger than the exact ground state. That's the necessary and sufficient condition. In practice, we usually don't do that. We say, here's a family of Hamiltonians, and we force ourselves to be bigger than the exact ground state for that family of Hamiltonians. But that guarantees us that there'll be some bad actors left over. And if these bad actors are left over, then that means that there'll be at least some systems for which we have gigantic errors, okay? So then we have to think, what are the objects where we do not have to do this approximately, right? What are the cases where we know in a practical form the exact constraints? And unfortunately, there are only 2, right? Well, okay. There's a trivial case, which is all the electrons are there. But that doesn't help us very much, right? We want to deal with a small system, not a big system, right? So there's only 2. There's the electron density. It's not a density matrix, but the irrepresentable conditions for the electron density are known. The in-representability for the, like, you already say, oh, I do 2 electron density. So the electron pair distribution, known, but only known in this sense, right? Only known in the sense of there is an infinite number of constraints. If you impose them all, it's okay. Here, the constraint is merely that the integral of the density is equal to the number of electrons, and the density is non-negative. That's all it is, right? This makes sense, right? And there are constructive ways of proving it. Like if you give me any density like this, an ugly one actually comes from the same Gilbert as the theorem we're just about to talk about, is just divide the system into pieces, each of which have 1 electron in them. Take the square root of the density in those pieces. That looks like an orbital. Take the anti-symmetric product of those orbitals. Done. Simple proof. It doesn't matter that it's not a good wave function. You just prove there is a wave function, right? And then the density matrix. So it's, we haven't really talked about it in spatial coordinates. We just write it as gamma PQ. Trace of gamma PQ equals N. So this was integration. This is now just the trace. You take the diagonal. The diagonals are like the probabilities. So this is the probability. So gamma PP is the probability of seeing an electron in orbital P, right? If I add up over all the orbitals, the probability of seeing an electron in it, I should end up with a number of electrons, right? So that makes sense. And there's several different ways of writing this. The simplest is this, right? It's nicer for hypothetical reasons to say that the eigenvalues of the density matrix are all between 0 and 1. But right, you can always diagonalize this, and then this is a diagonal matrix. So if any of the diagonal elements were below 0 or above 1, then this would not be true, right? So this is equivalent conditions. It's a little bit subtle, but they're equivalent conditions, right? This is the same as the theorem, right? That if I give you a matrix and I look at the diagonal of the matrix, the lowest eigenvalue is below the lowest element of the diagonal, and the highest eigenvalue is higher than the highest element of the diagonal. So we can only force the diagonal elements, or the eigenvalues between 0 and 1, we force diagonal elements to be between 0 and 1. Right? Okay, so now I'm going to clear things again, because I want to convince you, because I think it's a result that's often stated because it's totally intuitive, but rarely proved. So let's prove it. So this is my in-representable set, right? And I'm going to give you a bad guy, right? And we're going to prove what those conditions on the eigenvalues are, okay? So, what's the best way of writing this? Okay, so we have a one body operator because this is a quantity that looks like a 1 electron operator. So a one body operator in generically looks like HPQ, P dagger Q, right? I can always diagonalize a one body operator, right? So if I diagonalize a one body operator, so I'm going to diagonalize. I'm going to change the bases, so we'll just call it P tilde and Q tilde because I've now diagonalized it. And these elements we usually would call our orbital images, right? And now it's that delta. It's just convention. To give you an idea, a one particle thing is just orbital energy. So what is the ground state of this? Well, the ground state is you sort your orbital energies and you put electrons in the lowest n orbitals, right? So the ground state corresponds to just summing up over the lowest orbital energies, right? That's the ground state for a one electron, a non-interacting system. So with a one electron Hamiltonian, only one body terms in the Hamiltonian. Okay. Now, I promised you before that it must be that there's some system that can diagnose that this system is bad. Okay. So I'm going to think about a system that will tell you when this is bad. Okay. So I know that this has to be less than the true ground state energy for some system. And so there's going to be H gamma tilde has to be less than the ground state, which is just like this, right? Just the sum, let's use P. Just the sum of the lowest energies, okay? So now I'm going to just substitute. So what is it? What does this expression look like? Well, trace of this is going to be, I'm going to choose this sort of form. So I'm going to just say this is diagonal. So it's going to be epsilon P delta PQ. This is my density matrix here. My density matrix now has some elements, gamma tilde of QR. Okay, that would just be taking the matrix multiplication. But now I have to go back and I have to take the sum of the diagonal. So this is the matrix multiplication. And then I have to take the sum over the diagonal. And that's just summing over R delta RQ. So this now ends up being a sum over Q of epsilon P times, well, yeah, sure. We can just make this with the sum over epsilon P. Yeah, let's do it as Q. Doesn't matter because it's Kronecker delta. It's just going to be a little bit nicer if I do this. Okay, so this is my energy expression. It's just take the occupation number of the orbitals, multiply it by the number of the orbital energy. It's exactly what you would expect, right? I probably could not have derived. I could have just written it down and say, if you take the energy of a one-body thing, take the probability of seeing an electron in the orbital, multiply it by the energy of the orbital, right? And that'll be the energy expression. And I'm telling you that this thing is actually less than the true ground state, right? So how can I make this less than a true ground state? Well, one way I can make it less than a true ground state is I can put too many electrons in the low energy orbitals, right? But the low energy orbitals are supposed to have one electron in them. If I put extra electrons in the low energy orbitals, right? Then I can have a problem, right? So if gamma QQ is greater than 1 or Q less than or equal to N, then I can go below the true ground state. Okay, but I'm not allowed to do gamma QQ greater than 1. Now I understand why, right? That broke the condition. The other thing I could do is I could put a negative occupation in one of the high orbitals. And by putting a negative occupation in one of the high orbitals, I free myself up to put more occupation in below orbitals. So the other thing I can do is I can say, let gamma QQ be less than 0 for the high energy orbitals. You could also think of this as, imagine that you had an orbital that had energy of 100, If you put a negative occupation in it, then you get a big negative energy contribution. Right? But you're multiplying the probability times this. Right? So it's very intuitive result, but it comes out of the math too, right? That's the point of this. And it's this argument. This all we've done is we've just said, there's some Hamiltonian here that's going to help us separate this. So now, my last piece for this, right, is to think about the Gilbert theorem, right? So the Gilbert theorem is the Hornberg-Kohn theorem in this case. And it just says the one electron density matrix is enough, right? So why is the one electron density matrix enough? And this proof is exactly the same as a Hornberg-Kohn proof for people who are familiar with that, right? So, the easiest thing to do is I'm going to give you two systems. It's going to have gamma 1 and H1. It's going to be another system, gamma 2 and H2. Okay, so this is just like you normally set up and BFT-ish stuff, right? And let's go on while we're at it, and sure, we'll also just explicitly have size for system 1. It waits for. Okay. Now, it's helpful to remember that if I gave you sum over I, WI, the expression looks like some Hamiltonian one body part plus a two body part, right? I'm being a little bit sloppy with notation, but it's understood. This is the one body part and the two body part. Technically, what I should be writing is that this is a sum over for every electron. It's a different number for electrons. For every electron, you have to add up the same one body term. But once you do it in second quantization, it all goes away and it doesn't look that way anymore. So just not worry about it. Okay, and this is equal to the trace of H times gamma plus sum over I, WI, psi I, like this. Okay. So all I did is I just said, well, the one body part I can write in terms of the one body density matrix. I could have written this in terms of the two body density matrix. I'm not going to bother. This why. Right? Okay. So I know something. I know that the ground state of system 1 has the expression trace of H1 gamma 1 plus sum over I, WI 1, psi I 1, BEE psi I 1. And I know that that would be less than if I did the same thing, but instead of choosing the first system, I chose the second system, right? So variational principle says that this is less than H1 gamma 2 plus sum over I, WI 2. Okay. And I can do the same thing over again. I can say this is E ground state 2. H2 gamma 2 plus sum over I, WI two. Oops. I'm changing my notation in the middle of the stream. This.
Okay.
This is very much like Homer-Comter, right? You recognize the trick, right? Now, I'm going to just say, why don't I add these two things up, okay? But that's going to be really nice because this term showed up on the right side and the left side. This term showed up on the right side and the left side. So when I add them up, they all cancel out, right? So these terms will all cancel out. And I'll have trace of H1, gamma 1. Okay. So now we're in position for our essentially our proof by contradiction. I assume that there are two different density matrices, but they correspond to the same H, right? And if so, H1 equals H2, this is 0. This is the trace of 0, which is 0, but 0 is not less than 0, right? Therefore, if gamma 1 is not equal to gamma 2, H1 is not equal to H2, right? So this implies that H1 is not equal to H2, right? Right. So that's I mean, it's exactly the Hornberg-Kohn proof. I like this a little bit non-traditional because there's a really nice result, which is a generalization of this. It goes back to Mel Levy, and only in the DFT thing. I don't think he ever did it for the density matrices, but it's so obvious that which is that if I have a bunch of systems, K equals 1, so say big K, then so this is mathematical, but let's just say if I have a bunch of systems, if I pair the right one-body operator with the right density matrix, that's always better in energy than you would get if you permuted the indices, right? So I shuffled up the density matrices, and then I multiply by the one-body operator. So amazingly, even though technically there's not enough to solve a whole system here, right? If you give me a batch of density matrices and a batch of one-body operators, and you say, I know that these go together, I just don't know how they're matched up. You can always match them up by just minimizing the energy of the one-body term, right? So any shuffling of them will always raise the energy. It's a trivial thing. It usually gets buried in the Hornberg-Kohn proof, but it's the Hornberg-Kohn proof. Okay. Okay, next slide. Okay, so now we're in position to start talking about functionals because we're going to use this. This is my notation for this matrix. Its eigenvalues have to be greater than 0 and less than 1. That means it's positive semi-definite, and this other thing is just my notation to say its eigenvalues are less than, right? So it's just a notation to say I'm going to search over density matrices that are between 0 and 1 and that have the right trace. So Gilbert says that is enough to tell you everything about the system. Just like Hornberg-Kohn, the first order density matrix is also enough to tell you anything about the system. Even better than Hornberg-Kohn, right? Hornberg-Kohn said, given a kinetic energy operator and an electron-electron repulsion operator, the density, ground state density was enough to determine the whole system. Now we're saying something stronger. We're saying, I don't care what your kinetic energy operator is. I don't care, what your electron nuclear operator is. I don't care if you have relativistic terms in your kinetic energy, does not matter to me. As long as you tell me the electron-electron operator, this density matrix is enough, right? And this piece of the energy, we calculate exactly. We just see it over and over again. But there's a leftover piece that we were using the wave function for, but we know we can get it from the density matrix. We just don't know how, right? And already in the 1979 paper, the famous constraint search paper, Levy already did the density matrices also, right? It was really in the air in Parr's group at this point. So it was a logical extension. One thing to say is when you do this minimization, we can say that it doesn't say that there's only one density matrix at the minimum. If you have degenerate states, then you'll have many different density matrices. So you can prove that this is a minimum and not an infimum if the mathematicians care, right? But the minimum is not unique. I could fill in. So energy is concave in the Hamiltonian in the one body term. We believe it's convex in N for certain types of potentials, but not for every potential, right? Not even for the Coulomb potential, unfortunately, as we've learned in the last, 1 month or something like that, right? And then there was a more general formulation of this where instead we did this with, where Vallone did this for mixed states, right? And in this case also, the infimum can be replaced by the minimum. This functional is convex and the Levy functional is not convex. So I don't believe that the Levy functional is very useful. It was historically useful. I believe basically that the Vallone functional is the one that we're supposed to be using, right? And next slide. And I want to talk a little bit about the functionals now. So there's a reverse functional. It's called the Legendre transform. It's the dual functional. And it looks like this. We'll talk about where it comes from. It's no deep mystery. It's an easy derivation. But in this case, the supremum is not a maximum, right? So, and we can talk about why. Let's see how time goes. But basically, depending on the classic example is an idempotent. So any density matrix that has a 1 or a 0 eigenvalue, in fact, the supremum will be a supremum. There will be no maximum. Right? This functional is not differentiable, so that's also unpleasant, right? We like things that have derivatives. We talked about for kinetic energy last time, right? This functional is also not differentiable. Yeah, the counterexample is basically that whenever this is actually a maximum, but it corresponds to a degenerate state, then a very small change in the Hamiltonian will cause a gigantic change in the density matrix, and so there's no derivative. Right? And there's also a derivative discontinuity, just like in DFT. There's the integer discontinuity. So there's a bunch of properties of this functional which means it's inconvenient, but we're going to find out it's much worse than we expected. So we'll sort of defer some of this math for a little bit. Okay, next slide. Okay, so now we can talk about the functionals. So let's talk first about the Valone function. Okay, so this is the classic functional. So right, so the ground state energy for some Hamiltonian, some one body operator is just this, right? This is the same variational principle we've written before. You have to vary over the ensemble weights of the wave functions, right? And I'm going to just quickly rewrite this as like this, okay? So I just broke the Hamiltonian. These are linear operators. I just broke them into two pieces, right? So that I can now see that this is just the trace of H gamma, okay? So this tells me that this is now minimum over the weights and the wave functions of the trace of H times gamma plus okay. Nothing mysterious yet at this point. Now I'm going to do the constrained search trick, right? So I'm going to break my minimum into two steps, right? You know, there's a famous case in Parr's book for this, where he says, suppose you want to find, you know, the tallest person in a school, right? What you do is you first find the tallest person in every classroom, then you look only among the tallest people in the classroom, and the tallest person of the tallest people in the classrooms is the tallest person in the school, right? So the first search is just over classrooms, right? So we're going to do this. So we're going to say that our classrooms are the density matrices. So we're going to search over all the weights and the wave functions that give a given density matrix. And then we're going to search over the density matrices that are allowable density matrices, right? The occupation numbers are between 0 and 1, and the trace of the sum of the occupation numbers is the number of electrons. Okay, so we just break this into two pieces, right? Just like this. But notice that the density matrix is fixed here, which means this term doesn't change at all in this term, right? And this side is same whole minimum, this doesn't change. So I'm allowed to move this outside the minimum, and I get a minimum over Okay, so this is the Valone functional. You say, well, I'm going to minimize over all the possible ensembles, over all the possible weights and wave functions, right? I'm going to take their expectation value for the interparticle potential, the electron-electron repulsion, say, and that's going to be the Levy-Valone, the Valone wave function. Really. This is the constraint search over density matrices. This is the exact functional, right? We haven't said anything about how we should get it back, right? We'll talk about that at the very end, well, if we have any time. Yeah. Okay, so the other thing I want to say now is let's go back and I'm going to show you the other form of the functional, okay? So I told you that the ground state for some system H, well, it's less than or equal to the trace H gamma plus V of gamma. Let's say this could be Valone. There are other ways of writing the exact functional. We're just going to pretend it's the Valone functional for right now, okay? This is just the variational principle. It says if I put in the wrong density matrix, I'll get too high in energy. If I put in the right density matrix, I'll get back the exact energy. Okay? So nothing weird at this point. Okay, so let's just because okay, so now I just moved trace H gamma over to the other side, right? Right. So this is always too small, right? So if I just want to know what the right H is, then I should try to choose H's such that this thing is as big as possible, right? So I should try to make this as big as possible because it's always too small, right? So you do supremum. It's essentially a maximum, but with mathematicians' footnotes, okay? Just think of it as a maximum. Okay, so right now you'd say it's less than or equal to. I haven't guaranteed you, but on the other hand, I know that this was an equality if I had the right parent, right? And so we just get rid of the less than or equal to and say this is just equal to, and this is the Ayers-Golden-Levy version. Right? And that's just the functional. The derivation is that simple, right? It's even easier than the Valone functional, right? So now we need to think a little bit about practical matters, right? But we have two functionals. They turn out to be equal. Proving they're equal is more subtle, right? But it turns out that the Valone functional and this functional are exactly the same, right? They're exactly the same number, right? This functional is just a little bit easier to deal with in practice. And I think we'll talk more about that. Okay, next slide. Yeah. Okay. So I told you that this function wasn't differentiable at all. And this is a trick that Jose Luis and Umberto know very, very well, which is when you have a nasty functional, the correct thing to do is put in the temperature, right? So this now is a Boltzmann average. We put in some temperature, right? And this is the expected value of the energy, right? Instead. And so you could write this if you want. And this is now a nice functional, V tau of H, which is the supremum over H of, and let's just write it in a form that makes the most sense. It's the average energy of H instead of the ground state energy of H, right? This functional is smooth, it's differentiable, it's still convex, it's a beautiful form, right? Okay, and the next slide. And now we're into things that are more modern. There are other ways of doing this. So this corresponds to adding an entropy, right? This is gamma log gamma, right? The -1 you shouldn't worry about, it's just a normalization factor, so it's okay, right? But this is the temperature, this is TS, right? So you took energy plus TS and then you minimize it, right? That's the temperature formulation. And yeah, well, in fact, I already talked, I derived this formula already for us. Okay, next slide. Okay, and then this is what happens if you take the dual of this extra functional. So one thing that I think we'll talk about next time is we're going to talk about this in a little bit more depth. So I'm not going to even try it because we're running out of time already today. But it turns out that this is now a functional that's computationally practical, right? So we'll talk about how to actually do the computation. And rather than go through all of that, can you just go back, I think, 2 slides to a blank slide, basically. And then, yeah, this is fine. Thank you. Okay, so I just want to explain to you where these modern forms come from because it's an interesting trick. Okay, so there's a theorem or a whole field of mathematics dating from the 1800s, and what they call optimal transport. Okay. So optimal transport says, suppose I have a distribution, or just call it rho of x because it'll look familiar. This would be a distribution of mass. It could be a distribution of money. It can be a distribution of anything. And we'll just call this one rho 1. And then you have a different distribution, rho 2. And you would like to move things from rho 1 to rho 2 as efficiently as possible, right? So how would you do this? Or you would say, I have some cost function. Right? There's some mapping between x and y. So what's a mapping between x and y? A mapping between x and y is a function that says the probability that money at x ends up buying, you know, products at Walmart, Costco, 7-Eleven, wherever, right? So there's some probability that money at x goes to products at y, for example, okay? That's the cost, right? So there's some cost, and then there's a probability, and the probability times the cost is the total cost of moving whatever is at x. It could be density, it can be whatever, to whatever you want at y, to your output, right? They say, okay, so we're going to minimize this, but this quantity here isn't just anything. You can't just choose any distribution because there was an initial amount of stuff at x and an initial amount of stuff at y. So there's subject to the constraint, the integral of p of x, y, dy is rho 1 of x, integral p of x, y, dx rho 1 of y. And then, I mean, the normal 0 is less than or equal to p of x, y integral. Right? The normal thing that says is a probability, right? So this is the classical optimal transport. This is just 1800s math, okay? So maybe not obvious why this is really interesting yet, but now let's think about quantum optimal transport. So I should start by saying they call it quantum optimal transport. Quantum optimal transport just means everywhere you solve a function, replace it with a matrix, right? So that's what they're doing. They're saying everywhere you see a function, replace it with a matrix. Something they call it non-commutative optimal transport, because in classical, like normal algebra, you can multiply two things, and if you swap their order, it's the same. And with matrices, this is no longer true, right? But they call it quantum optimal transport because if you call it quantum optimal transport, then you pretend it's quantum computing, then you get lots of money from the grant agencies. Salesmanship, right? So we're going to do the analog of this, right? The application is going to be much less clear, right? So what we're going to have is we're going to have some cost. Well, it's going to have two indices. It has P1, Q1 going to P2, Q2, okay? That's our cost matrix, right? Just because every variable before I replace with a matrix, right? So there's two corresponding to gamma of P1, Q1, and then I have gamma of P2, Q2 that is coming out on the other side, okay? Now I have to put in something that's going to depend on all of these variables. I'm going to minimize it subject to a constraint that trace over 2 gamma. Okay. Okay. I've been sloppy with my indices and everything, but the goal is to say that this is the analog of this, okay? So all I did is I replaced variables with matrix indices. Now, still maybe not obvious that this is what we want to do, but let me just rewrite something in a certain way that I think will make it all of a sudden make sense to us. If I say what I want to do is minimize the trace of V times gamma, subject to a constraint that the trace over 1 of gamma is gamma. The trace over the second part of gamma is also gamma. And in general, you could say the trace over any piece of the ensemble is equal to the same 1 electron density matrix. And then this is then all I've done is I've traced over my entire ensemble, subject to a constraint that it gives back the right 1 electron density matrix. And I chose V, which was my potential, to be my cost function. So this is exactly V Valone of gamma, right? So now it's been rewritten in terms of this fancy optimal transport mathematics, okay? And this basically ends up being the key thing. So we talk about this next time. We talk about why this is actually useful. Okay. Okay, well, I just finished, so that was perfect. So no time for questions. Thank you.
We have 1 minute for one question.
I'll answer them in the halter. So,
Okay. Do you have question?
one burning question, they can't wait for next time, yeah.
This last part can be used for example, if I have a distribution in position and I have the other one, or I want to find the other one in momentum, or is not for that?
It can be used for this. It's probably trickier than you think, but it can be used for this. Usually they do one position momentum going to a different position momentum, but you can use it like this.
Okay, so thank you, Professor Ayers. So looking forward to see you everyone in the next section. Thank you. Bye.